Hello and welcome to week 5 of the online particle physics course. Last week we spent the whole week discussing about a double slit experiment. So this was our double slit experiment in terms of waves, and we saw that schematically we could represent it like this. We also saw that we had a formula which was delta equals to d sine theta, and we had an interference condition which was nothing but d sine theta equals to m lambda. Okay, I think you should revise all of this if you did not understand it properly. So going forward, we'll just remind ourselves what the intensity pattern is, and we will attempt to answer all the questions that were raised last class. So we ended the class with the interference using electrons, and we saw that this was the interference pattern that we got. So we didn't expect it. Electrons we always knew were particles, and particles we knew do not interfere. It's only waves which interfere. And this the emergence of this pattern raised several questions. One of the questions was, how could electrons be both particles and waves? Okay, and if they are really waves, what waves are they? Are they something like water waves? Are they electromagnetic fields? Okay, what waves are they? Obviously they are not water waves. Whether the electromagnetic fields or not, it's very unlikely. Light is wave. Light is a wave, and it's basically electromagnetic field which is waving. The electrons are different, not light. So if there were electromagnetic fields, you would get light. Then light and electrons would be the same. So it's not electromagnetic waves. So clearly these are strange types of waves, if they're waves at all. And in this week's lecture, we'll try to address some of the issues, and we'll see that the answer that we can arrive at, it's a pretty strange answer. Okay, so in order to arrive at that answer, we will pursue something called Feynman's thought experiment. Now this was a thought experiment which was most clearly elucidated by Richard Feynman, one of the great scientists ever. And Feynman, in his very famous series of lectures, this was in 1964 in Cornell, where he gave a series of lectures, and they are recorded in a book. They're called Feynman's Lectures on Physics. And he, in third volume of that series, he explained his thought experiment, and the thought experiment is really the double slit experiment. Now, a thought experiment is an experiment which you can argue out the consequences. You surmise the result. You think what the outcomes might be. You don't actually do the experiment because it's just too difficult. So in principle, what should happen is the experiment. So it's an experiment done in the mind. Okay. Obviously, these do have experimental basis, but in 1964, when this was thought out, it did not have an experimental basis as well as we would have liked. So we'll just surmise the result. Now, the thought experiment is really a double slit experiment. Okay. Now we performed the double slit experiment using light in the previous class, and right at the fag end we did it using electrons. And this time we'll do the double slit experiment using three different things. Now the setting is just the same. We have a source. This is the source, and this is the barrier with the slits, and then there's the detector behind it. Okay, and we'll be using as the source. We'll be using the first. We'll be using bullets. So these are just bullets from a gun. The bullets that we can think and often see. And the second will be with light. Again, this is the experiment that we had done last week, and just repeat that for completion. And the third will be with electrons. So we saw what happens when we do it with electrons, but we'll see what happens in the thought experiment. Obviously the outcomes will be similar, but we have to interpret it in a particular way. As and when we can, we will modify this third experiment, that is the experiment with electrons, with different detectors. We won't do this in this class because it will be too heavy, but we'll see how we can go forward with that. Okay, So the first one is with bullets. Okay, so you have a mad gunman with a gun, okay, and he's spewing up bullets, the large angular spread. So the bullets don't come out. He's obviously not a marksman, is not a sniper. So, and the gun that he has is the machine gun. It's not a sniper rifle either. So the bullets come out with a large angular spread. It comes out over a large area. Okay. There is this barrier in the middle, which is made up of, say, very strong armor, so the bullets can't penetrate it. And the screen has this detector. Okay, but the detector is movable. Okay, it might be a sandbag or something like that, which will absorb the bullet if the bullet hits it. The bullet hits the sandbag, it's absorbed. So we can keep the detector over here for some time. It will absorb some number of bullets. We can empty the sandbag, count the number of bullets, and then put the put the detector back, and we relocate it to some other place. Okay, and then again some bullets will come and hit, and we can repeat the procedure. Okay, so this is how we are going to test out how many bullets hit each of these each point on the screen. Okay, now you have to assume that the bullet is completely indestructible, so whenever it hits the armor or whenever it hits the detector, nothing happens to it. Okay, it can just bounce off without breaking. Okay, now the experiment is really this: you close out one of these slits, so that just one slit is open. You close out one of these slits and see what pattern you get. So this is how the bullets will travel. They'll hit the screen, they'll hit the slit, and then they'll hit the screen after some time. And the pattern that you should get is something like this. So let me just explain the pattern. So you see the blue line over here? The blue line is with this lower hole open and the upper hole closed. Okay, so this we'll call, so if we number these holes 1 and 2, so this is just I2. I2 means the bullets come only from the second hole and the first hole is closed. And similarly, this purple line is again the distribution that you'll get with the lower hole closed and the upper hole opened. So we see something which is quite commonsensical. We would expect that, and that is, if we have one hole open, we will see a bump. The distribution will just be a bump behind that hole. And similarly for the other one. So if you open the first hole and close the second one, you will get this purple bump, and if you open the second hole and close the first one, you will get this blue bump. Okay, and if you open both the holes, what you will see is that these bullets just go through this, form this bump. Some bullets go through this, form this bump, and there will just be an addition. So I've just dotted these lines out. This is just the blue bump which comes, and this is just the purple bump which comes, and this yellow bump is the bump which you get when both the holes are open. Okay, so this one is I1 and I2, which are just the intensities with the first hole open, the second hole open. This is just I12, which is just addition, which is the resultant intensity. Okay, I12 is just the resultant intensity. And now these intensities are obviously related to the probability of the bullets going through and hitting one part of the screen. Obviously, if some part is more probable to be hit than the other, it will show up in the intensity. So we can just replace intensities directly by probability. So if this is a probability and this is another probability, this probability distribution. These are just functions which tell you where the probability is high, where the probability is low. For example, here the probability is really high if you open the first hole, but probability is really low if you open the first hole over here. And similarly with the second hole, the probability is really high that the bullet hits here, but the probability that the bullet hits here after going through the second hole is really, really small. And if you just add them up, then you just get this kind of a function. And these graphs are again plotted with Mathematica. I've used a particular functional form and plotted them. Okay, so that's that. There's nothing much to it. This is more or less commonsensical. So we'll just summarize our experimental findings, and we see that the bullet is a classical object. It just passes through one of the slits and then hits the detector on the screen. Okay, and we saw that this detector is something like a sandbag. We move this detector around and collects bullets, and we know, well, since we know which slit is open, since we know which slit is closed, we can know, we can plot that product distribution. Obviously the bullets are indestructible, so they all appear whole. You don't find half a bullet anywhere, and this will be important as we go along. For bullets it's obvious, it's quite obvious, but for light it might not be. The intensity is related to the probability, obviously, as I explained right now. If there is a particular portion of the screen which is more likely to be hit, that means it has a higher probability of being hit, it will show up in the intensity, as in more bullets will hit the screen over there. Okay, so intensity and probability are really the same physical quantities. We can just replace one by the other. That's just up to a certain scale, up to a certain number, they're just the same. Okay, the intensity and or the probability over here, they just add up. Okay, and we know that there is no interference for the bullets, because the interference pattern is very, very different from this kind of a pattern. This we saw last week, right? So just to summarize everything, the bullets appear whole, the probabilities just add up, and there is no interference of the bullets. Okay, pretty commonsensical. I hope all of you agree and all of you are comfortable with this. Next we go on to the experiment with light. This was the first part of the experiment. Next we do it using light. So experiment using light. So we have a point source of light. Okay, and again we have this movable detector which detects the intensity of light at every point. Now this is obviously not a sandbag. This is some light detector, something which detects light. It can even be the eye, but the eye doesn't have a quantitative measure, like how much light is being detected. So we'll use a certain detector which can detect how much is measured. So this can be any photo detector. Okay, and the detector detects the intensity of light, right? So if the detector detects the intensity of light, it detects the square of the amplitude. We saw this last one. The intensity is the square of the amplitude, is related to the square of the amplitude. Okay, and the intensity is obviously related to the probability. Okay, so here we have this same apparatus, and instead of bullets we have light going through, and we saw that this is how it goes through. And this is the pattern that we get if we close one of the two holes. So again the purple one is opening the first hole, closing the second one, and the blue one is closing the first one, opening the second one. But we saw this last time that if we add them up, and this is the property of waves, if we add them up, they follow this kind of an intensity, which is nothing but the addition of which is nothing but both the holes being open. So if both the holes are open, light can go through both the holes at once, which is what interference is. Okay, light goes through both the holes at once, then light coming out to this first hole and light coming out through the second hole, they interfere, they add up. Okay, so the intensity here is I1, I2, and the intensity here is I12. This is not the summation of I1 and I2. We saw this last week as well. The intensities are not the summation. Okay, it's true for bullets, it's not true for light. Okay, the intensities are different, and the probabilities also is just not an addition. Okay, and we know why that is the case. We know that is the case because the detector can detect any intensity of light. Okay, it can detect anything, so it can detect from the highest to the lowest with all the values in between, and it detects that kind of a pattern. And we know that the intensities are not getting added, the amplitudes add up, and then we square them. So the addition is happening at the amplitude level. Remember that the addition was happening at the wave level last week. So it was y equals to y1 plus y2, and the intensity was y1 plus y2 whole squared. It was never y1 squared plus y2 squared. It was y1 plus y2 whole squared. There is an interference term there. So this just confirms what we already know, and what we know is that light has a wave nature. Okay, we derive something from this thought experiment. We arrive at a very, very important point. The point is that light has a wave nature, and it's not the probabilities or the intensities which are getting added, but the amplitudes which are getting added. For the bullet experiment, we saw that the probabilities were getting added. So this is at the level of the probabilities. the summation for light happens at a level lower. Probabilities are squares of the amplitudes, and for bullets that's where they get added, so they are squared first then summed. For the light experiment, you have first summation then squaring, so the summation happens at a level lower, and that is at the amplitude level. So we just know, and this is always true when we are dealing with waves, we know that. So just summarize, so the light intensity can be anything from 0 to maximum, which is very different from what we got in bullets. Bullets, you had 1 bullet or 0 bullets, so you could count individual bullets. You had 0 bullets, 1 bullet, 2 bullet, 3 bullet. You could not have a 1.5 bullet because bullets were indestructible, right? Light, you can have any intensity. So if you just go back, you can have an intensity from anywhere from 0 here, okay, to the maximum, and depending on where you are, you could get any intensity you wanted, right? So so light obviously has wave nature, and you have interference, and you can get intensities up to from 0 to maximum. The probability is the sum of the amplitudes. It's the square of the sum of the amplitudes. It's the square of the sum of the amplitudes, and the crucial thing to remember here is the amplitudes are summed and not the probability. So it's first summed then added. First summed then squared, and this leads to interference. Right? This does lead to interference. So this is the expected wave behavior. So first one was bullets, now it's light, and we have cleared both flying colors. I'm sure bullets was completely commonsensical. Light, I showed you last week, even if it's not commonsensical to start off with, you know why it happens. You know that waves add up at the amplitude level and then you square it. So this is what we did last week, and we're just using that knowledge. Okay, so this was the second part of the thought experiment. So we have a double slit pattern, we have used bullets as our candidates, use light as our candidate, and now we're going to use electrons as our candidate. So we repeat the experiment with electrons. Okay, now here we have to be very careful. We have to define a lot of things because we have not done this before, so we have to define a lot of things. So there is an electron gun, which is a steady source of electrons, and the electron gun can emit a lot of electrons at once, or it may emit one electron and then wait and then emit another electron. Doesn't really matter, but there is an electron and it's a steady source. Electron gun is a steady source of electrons. So there's an electron 1 second, there's an electron the next second, an electron the third second, and so on and so forth. Okay, the detector is obviously again movable. So here you have the experimental apparatus. The detector is obviously again very movable, and when electron hits the detector, okay, it produces a sound like click. Okay, hits the detector, is like click. Another electron hits the detector, click. So every electron hitting the detector will have a click, will produce a click. The loudness of the click tells you how much energy the electron is carrying. Okay, so electrons start off with an energy E, and it hits the screen with that energy because there is no energy source or sinks. There is no way to gain energy or lose energy in the middle. So you would expect that the energy with which it hits the detector is more or less the same. Okay, round about the same as what it started off with. So when it hits the detector, it produces a click. Okay, and it can be that some electrons hit the detector with large, if it does, is a large energy, it would produce a loud click, and if some electron hits the detector with very low energy, it will be a very soft click. But as we just argued, electrons do not gain or lose energy in the interim. Okay, the slits hardly interact, so they don't gain or lose energy while traveling from the source to the screen. All the electrons hitting the screen will produce the same loud same loud click. Okay, so you won't so if two electrons hit the detector at once, okay, which is a very unlikely event. But say if 2 electrons hit the detector at once, you will produce a click which is twice the loudness as with 1 electron. Okay, if you somehow conspire, and it's extremely unlikely, but if you can somehow arrange for 3 electrons to hit the detector at once, it will produce a click which is 3 times as loud as if 1 electron hits, right? So what is the probability? Now, we did this last week, the final experiment, okay, and if you leave one of these slits open, you will get this kind of a pattern. Okay, this is the same as you get with the bullets. Okay, so leave the first slit open, you get the purple. Leave the second slit open, you get the blue. Okay, this one is the pattern you get if you leave both the slits open, and that is a big surprise that we found last week. Electrons are not supposed to do that. Electrons are particles. They are not supposed to form wave-like interference, but they do. But this is a wave-like interference with a huge difference. So this one is I1, I2, and this one is I12, okay, and which are related to P1 and P2 and P12. Now you might say, okay, then electrons are like light, they're waves, but they're not, because when you listen to the detector detecting the electrons, the detector goes click, pause, click, click, click. There is a small pause after every click, and there is a certain there's a certain loudness of the click. So the click is of uniform loudness, and then there is a pause between 2 clicks. So it is obvious that the electrons are hitting the screen one at a time. It's like a bullet hitting the screen. It's not like a wave. It's like a bullet hitting the screen. So a bullet goes and hits the screen, and it produces a click. Okay, an electron goes and hits the screen, produces a click. Nothing happens. Another electron comes and goes and hits the screen, produces a click. And by positioning the detector properly, you know where the electron is hitting. Okay, but if a large number of electrons hit the screen, you form an interference pattern. Okay, please understand the paradox over here. The paradox is that when it is hitting the screen 1 electron at a time, it is behaving like bullets. Okay, you are getting the same sized clicks with pauses in between, just like you would expect for a bullet. You fire a bullet, goes through, hits the detector, you register it. Next bullet goes through, hits the detector, register it. Electrons behave in exactly the same way. It goes through one of the 2 slits. We don't know which slit. Even for bullets, you did not know. So here you don't know which slit it goes through. Goes through the slit, hits the detector, produces a click. Next electron goes through the slits, hits the detector, produces a click, and it goes on like this. It's click, it's click, 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 and there is a finite pause after every click, and the clicks are all of uniform loudness. These are just like bullets, except that they also behave like waves, also behave like light if you allow a large number of electrons to fall on the detector. If you have a large number of electrons to fall on the screen with the detector at various points, you will find that the probability really doesn't add up. Okay, the probability distribution is like a light, is like light, is like a wave. So the electrons obviously interfere with each other, but they arrive as particles. This is nothing like what we have seen. This is not like bullets. This is not like light. Okay, it's somewhere in the middle. It's a bit of both. This is the ultimate paradox. This is how an electron is, and we don't know why. Okay, so the results of the electron experiments are very non-intuitive. So we have known that the electrons are particles, okay, because we have seen that electrons get deflected in a magnetic field, etc. Now we might think, okay, electrons are particles, we will treat this as particles. We will try to explain this using particles because the particle description has worked so well. Okay, now can you produce an interference pattern using particles. You detect an interference pattern. You try to explain it using particles. You say, okay, I will stick to the particle dogma and produce that interference pattern. Okay, you say, okay, maybe the electrons just break off. Maybe electrons are not whole particles. They don't arrive at the at the detector as whole particles. Maybe they break off and half an electron arrives somewhere, half an electron arrives somewhere else. Okay, so they break off at the slit and arrive at different positions on the screen. But remember, that would affect the click of the detector, because if an electron can break off, okay, into say two parts, it can break up into many parts, but say if it breaks up into two parts, then one part will be carrying half the energy, another part will be carrying the other half of the energy. Okay, or there will be a distribution of the energy. It will never be the whole energy with the one part and zero energy with the other part. So the click of the detector are all of the same size means that the whole electron arrives. There is no half electron, there is no 1/4 electron, there is no 1/4 of an electron. The electron arrives whole. So the first attempt, the electrons breaking off and arriving in different positions in different fractions is completely ruled out, because the size of the clicks tell us otherwise. So clearly the electrons don't behave like bullets. Okay? They do show interference, but then they are particles. So how can they behave like particles? So you say, okay, maybe the electrons go through slit A or slit B, is the hypothesis, but then you test it out. Okay, and you test it out with one slit closed, and you see that you get the normal bullet-like pattern. You shouldn't get the normal bullet-like pattern. Okay, you should be getting the light-like pattern, but you don't. You try and set this up such that you either either close one slit or you close the other slit, and then you try to add up the probabilities. They don't work. For particles, you always have to add up the probabilities. So the conclusion is that the size of the clicks never change. Okay, the click is of the same size, which means the electrons don't split. We saw this in case of bullets. The bullets always appear whole in the sandbag. We did not see this in case of light. Light, remember, could take up, the intensity of light could be anywhere from 0 to the maximum. Okay, the intensity pattern, however, doesn't suggest that it's a particle. It refers it suggests that it's a wave. The intensity pattern, that is how strong that that intensity curve that I showed you is, just refers to the number of electrons at a certain point. Okay, so if you keep a detector at a certain point, it detects a lot of clicks, then it's high intensity pattern. Okay, the electrons can impinge on the detector as particles. We just discussed that they impinge on the detector as particles. They make a click when they impinge on the detector, but it seems that they also show interference when they come in large numbers. So we have a problem, and the problem is that electrons, we knew this problem from last class itself. The problem is that electrons seem to behave both as particles and waves. Okay, that is a big problem. So is there a simple mathematical interpretation to this? Physically it's very difficult, but is it possible to interpret this mathematically? Okay, and it turns out that mathematically it's extremely simple. Okay, it's just addition and squaring. That's very, very simple, and we have known this since the days of light experiment using double slit experiments. So the electrons are individually particles. That is the conclusion we are forced to. They're individually particles, but the distribution is like a wave. They're distributed like a wave. So they arrive at a particular point like a wave. Okay, they travel like a wave, thus they interfere. Okay, because they interfere, they produce that interference pattern. So they travel like a wave, they're distributed like a wave. Okay, what that really means is a very, very dicey question. Okay, so the next question which you should ask is, I am willing to accept that there are waves, but what are the waves of? For example, light is a wave of electric field, electric and magnetic field. What are electrons waves of? Are they electric fields? It turns out that electrons are not the same kind of waves. The electron can be described by a probability wave, and we are just waving our hands and saying, okay, we cannot come up with something better. We say that an electron is nothing but a probability wave. It has a wave with it such that the amplitude of the wave describes probability amplitudes. Okay, we saw that the amplitude of the light wave described the amplitude of the electric field, right? And we took the square of the amplitude and we got the probability density, and we took probability intensity, which is the probability density, right, last time. So so for light, the amplitude refers to the amplitude of the electric field, and we square that and we get the intensity. Here, the height of the wave, the amplitude of the wave refers to the probability amplitude. So at each point you'll find out what is the probability, and then you square it up to give you the probability density. So intensity is square, so probability is a square of the probability amplitude. Okay, it's just the same. So intensity and probability are definitely linked. We saw that right in the early portions of this class. So if you have a wave which has an amplitude, the square of the amplitude is the intensity. So if a wave describes just probability, then the square of that probability is the probability density. Okay, so the electron waves add up, which means the probability amplitudes add up. Okay, it's the square of the wave, and it's only after addition that you square it. Okay, and P12 is just not just P1 plus P2, so they're not ordinary bullets. They are bullets which arrive like bullets, but they still interfere. Okay, now obviously this seems a bit odd, and we would like to ask the question, how are electrons different from light waves? And we've already got part of the answer. We're saying they are these ad hoc waves. Right at this point, they're just ad hoc waves. Okay, and just probability waves, they're not real. I mean, we can't detect probability waves because they are not, you're not detecting something physical. Okay, you can detect a probability, but you can't detect probability amplitude. We'll come to this point in much more detail later on. So a light is actually, as I've been telling you, it's just fluctuating electric and magnetic fields. It's electric and magnetic fields which do the waving. So they're just waves of electric and magnetic fields. But the electron waves are nothing like that. There is nothing which is tangible that is waving. Okay, there's nothing waving. We can't say that, okay, if you put an apparatus here, you will measure this thing waving. There's nothing like that. They are just probability waves. They are different kinds of waves. They're new kind of waves. So these are probability waves. They represent probability, and they are not represented by real numbers. They're represented by complex numbers. Okay, so if you are versed with real numbers, you will know that there is something called a real number line. So 1, 2, 3, 4, minus 1, minus 2, all the fractions, everything are just real numbers. Okay, complex numbers have this peculiar property. So real numbers have the property that if you square them, the square is always greater than 0. Okay, there is another type of number called the imaginary numbers. I'm sure you've heard of it. If not, we'll have short introduction to imaginary numbers and complex numbers next class. Please tell me if you have not heard of it in the comments to this blog post, and we can have something on imaginary numbers and complex numbers next class. The waves are well, these are not real numbers, so the square of the wave need not be positive. Imaginary numbers, the square of an imaginary number can be negative. Now the square of nothing can be negative, okay, except for imaginary numbers. The square of nothing, nothing real can be negative. So if you take minus 2.4, you square it up, okay, you get 5.96, which is greater than 0. But for imaginary numbers, the square of them can be actually negative. Similarly, for complex numbers, square of a complex number can be negative. So we will not take the square of a complex number, we'll take something called the mod square of a complex number. If these seem very very unnatural, and if you're not familiar with them, please tell me. We'll have a short discussion session on this in the next class. The great thing about using complex numbers is this: in an experimental apparatus, you can never measure complex numbers. Okay, so you can never measure the wave itself. The wave is a complex number. Okay, you can never measure the wave itself. It's only when you mod square it that you convert that into a real number. Okay, so when you mod square a complex number, you get a real number, and that real number is something that you can measure. So you can only measure real numbers in an experiment. This is a very, very crucial concept. So you can never measure complex numbers or imaginary numbers in an experiment. You can only measure the real numbers in an experiment. The wave is a complex number. Okay, it's a complex wave, so you can never measure it. But if you take the mod squared of it, okay, then you can measure that. So let me just explain it a little bit better. So you have a probability amplitude which is complex, so you can never measure the probability amplitude, and which is just as good, because you cannot, as I told you, there's nothing real weaving, so you cannot put an apparatus somewhere and say, okay, this is weaving and this is having this kind of amplitude. That is not possible. Okay, but if you take the mod squared, you can measure the probability amplitude, and the probability amplitude is what matters. Okay, we are really not interested in the probability the probability intensity. We're really not interested in the probability amplitude. We are interested in the probability density. Okay, the probability density is the mod squared, and you can always measure the mod squared because the mod squared is always a real number. Okay, in fact, it's a positive number, positive real number. You can always measure positive real numbers in an experiment. Okay, so this is kind of good for us, and it's kind of needed. So let's just take an example. Let's just take a very simplistic example. Let's say the electron wave, this kind of special wave, is just spread out in one dimension. Okay, and the square of the wave at each point. So you take a wave at a point and you square that up. You take the height of the wave and square it, and that gives you the probability of finding the electron at that point. Okay, now that does not make too much sense because the point is a vanishingly small region, so it doesn't really make any sense. So what you say rather is that, so if there is a wave function, okay, which is basically the probability amplitude, describing probability amplitude, and it's denoted by psi. So psi of x is the function which describes the probability distribution, the probability amplitude, sorry. Then the amplitude of the wave at the point x naught is psi of x naught. Now psi of x naught is the probability. Then probability of the psi of x naught is not the probability, it's the probability amplitude. Okay, so the probability of finding the electron in a small region delta x, which is extremely small, around x naught, delta x around x naught, which is like really small, delta x is really small, is simply given by psi of x naught, which is the probability amplitude at x naught, mod squared. So this is a real number. This gives you the probability density. It's something like the density, the relation of density and mass. So it takes out the probability density. Okay, now the probability density is fine. You multiply that by this small number and you find the probability of finding the electron at x naught. So right now, probability of finding the electron at a point really makes no sense, but probability of finding the electron at a point and a small region around the point makes some sense. So you have to multiply it by this delta x. So this is the probability density, and you multiply it by small delta x, and you get the probability of finding the electron at x naught. So again, repeat. Electron wave measures, electron wave is the probability amplitude. The mod square of the wave measures the probability density. And the probability density itself multiplied by a small region around it gives you the probability. It's probability, it's density, right? So density and probability are linked by a small factor, which is the length the length over which that is taken. So this is more of a technical point. We assume the function to be regular and smooth. This is for people who might be finicky about the math. Of course, if this function were a wildly varying function, we couldn't write that, but you can ignore that point for the moment. And we have to start from here. So this is the starting of quantum mechanics. There is nothing deterministic anymore about quantum mechanics. So a couple of philosophical points, if you may, at this point. We will see that quantum mechanics is the real theory of nature. Okay, there's nothing apart from quantum mechanics. Classical mechanics has its limitation, we saw that, and we were introducing little bits and doses of quantum mechanics into the classical physics that we knew in order to explain phenomena. But then you want to reframe the whole of the quantum mechanics at one go. So you take this new approach. You start from this abstract wave formalism, which is nothing but a probability wave, and you take the mod square of that, you find the probability, and everything is at the level of probability. So whether there is interference or not, it's always probabilities. So the observables are really probabilistic. So it's not like ball thrown up. Okay, in the quantum mechanical world, if a quantum mechanical ball were thrown up, it might go up, it might go down, it might go sideways. In the classical world, that's not true. The classical world, it's always true that the ball will come down. The difference between the two is that in the quantum world, if a microscopic ball, say an electron, is thrown up, it has a high chance of, it's the high chance of coming down, but it also has a finite chance of going up or going sideways. Okay, in the classical world, there are these particles which are all governed by quantum mechanics, if you might say. So the particles of the ball individually are all governed by quantum mechanics. All of them have a very high chance of going down, okay, coming down back to the earth. Okay, now they also, or each of these particles also has a chance of going up or going sideways. Okay, there is always a finite possibility, but that possibility is really small, because each of the particles has a very high probability of coming down. Okay, so we have never seen anything, a ball going sideways or up after being thrown up, because there are so many particles that are there in the ball. Okay, it is highly improbable that the ball will go up or sideways. Okay, but we can never rule it out. So quantum mechanics is like that. Quantum mechanics says that you can calculate stuff, but you can never calculate stuff with 100% certainty. In most cases we can't. There are certain cases in which we can say something which is of 100% certainty, but in most cases you can't. So we can only calculate probabilities, and we can only make predictions in probabilities. Okay, we can say, okay, 80% of the time this is going to happen, 20% of the time something else is going to happen. Okay, so has science and has physics given up on calculating exact numbers and started to calculate probability? And in a sense, yes. Is this progress? Yes, it's progress. But we really cannot calculate something. In most of the cases, we cannot calculate something and say this is the only outcome, and then there is nothing else, and this will happen 100% of the time. For example, you can never say that the electron that you are launching from the electron gun earlier, you can never say that it won't go to Jupiter. Okay, it might just go to Jupiter. For a bullet, you can always say that. For a bullet is a classical object. A bullet, there is no way that the electron can go to Jupiter, that the bullet can go to Jupiter. It will hit the screen. But an electron, you're not sure. Okay, so the observables are all probabilistic. This is an important, very important statement. Science, physics has kind of given up on calculating exact numbers, deterministic numbers. So this is a big shift in the philosophy of physics, from Newton and Galileo and even Einstein to this kind of new physics, which was championed by Dirac. Einstein in the early days, and later on he despised it. Um, Schrödinger, Heisenberg, later on Feynman, all of them champion this kind of physics, and this is the real physics of the world. And this is a small introduction to that physics of the world. So what it really means graphically is something like this. So say we have a psi of x like this, and the psi of x is the probability amplitude. And I've just taken this function and squared it up, and forget about these values. I've just taken this function and squared it up. It's done Mathematica, so Mathematica gives a scale. And so this is the probability amplitude, and this is the probability density, just a square of this, mod square of this, remember. Sorry. And this is the point x0. I forgot to mark it. This is the point x0. This red line which is going up, this is the point x0. Okay. And you take a small sliver around x0. We saw this. We take a small sliver around x0. So let's just revisit this formula. So you have a point x0, and the wave function is psi of x0, and the height of the square of the wave function is psi of x0 squared. So we just go back here. So this is just psi of x0, and this part is psi of x0 mod squared. This is your probability density. So this is the probability density, and you and you multiply the probability density with the width of this region. Okay, so if you multiply it with the width of the region, what you get is this sliver, this area, this blue area that you have. Okay, this sliver, that is the area of that small the small strip. So that sliver is the area under the curve, okay, for this width delta x. Okay, and that is the probability. So the probability is really the area under the curve for that width, and this is a continuous probability. Okay, there is no discrete probability involved, so it's not like 50% here, 50%. It's a continuous curve. Okay, it's not like you have one line here, one line here. It's a continuous curve. We'll not dwell on that too much right here. So you have a probabilistic description. So you will say that, okay, the chances of locating an electron which has a wave function psi naught at x naught is psi naught squared mod psi of x naught mod squared into delta x. So this is really too long a sentence. You can't say that. So we'll invent some new notation, and we can't keep on using language. Language is a very bad way for doing physics. It has to be mathematics. So we'll have to invent a new notation. We will invent in some time. We just won't bother with it right now. So this is what it means. And so we come to this new world view, and the world view is that there are these wave functions which are psi's, and they're related to the probability. And the probability of an event happening in an ideal experiment is given by the square of the absolute value of the complex wave function. So your psi is a complex wave function. It's not a real function. You can't measure psi. Okay, and you mod square it. Okay, you take the absolute value of that, mod square it. If you do not know what that means, tell me in the comments. I repeat myself. We will discuss this next class. And this represents the probability amplitude. The wave function represents the probability amplitude, and the mod square represents the probability density. So this is the probability density of this. This P is the probability density. We often interchangeably use the words probability density and probability, even though they're not exactly the same. Obviously not, but we often use them interchangeably. It's not quite correct, but we'll do it. So if an event can occur in several alternative ways, it's like the light can go through slit 1 and slit 2, and at a certain point, so light goes through slit 1 and slit 2, and you detect on the detector on the screen the intensity of light at a point. You cannot know whether it came from slit 1 or slit 2, so the end result is indistinguishable. The end result being indistinguishable, which is like the electrons arriving on the screen. How an electron arrived on the screen, you cannot see. Okay, so you take an electron, take a particular part on the screen, and an electron hits that. You cannot say whether it came from 1 or 2. If you cannot say if it came from 1 or 2, then you add the wave functions. You add the probability amplitudes. The total probability is then the square of that sum. Okay, it's not like bullets. bullets are different. So if an event, this will be our this is like a new world order kind of thing. uh, so if an event can happen in several alternate ways, and this is an extremely important statement, if an event can occur in several alternate ways, then the end result, such that the end result is indistinguishable, you add up all the ways in which you add up the amplitudes, add up all the ways in which the event can happen, and then you square it to get the total probability. Um, if an event can happen such that the alternatives are can be distinguished. Okay, if you can distinguish one alternative from the other, for example, if you if a bullet arrives on the screen, you can almost surely tell which slit it came from. You can almost surely tell which slit it came from. Then the interference is lost, and you just add up at the probability level. Okay, if an event can occur in several different ways, you cannot say at the amplitudes an event can happen in several ways, but you can say how it happened. Then you add up the probabilities. Okay, this is extremely crucial. Knowledge of the ability of whether you can actually say how the event happened gives you a big change in how you determine the probabilities. Okay, nice. So we asked a few questions from last class, and the questions were what kind of waves are electrons? Can we see electron waves? We asked whether electrons can both be can be both particle and waves at the same time. If not, then which one is the correct description? And we also asked what the wave function is for the electron. So we kind of have answers for this, and I had promised you answers for this. We kind of have answers for this. And the electron are complex waves. They are called de Broglie waves. Okay, de Broglie is the name of a scientist, Louis de Broglie. So they are just complex waves. They are waves which determine which indicate probability. And no, we cannot see probability. If we cannot see these probability waves, we can't see electron waves. Okay. So Louis de Broglie, while he was thinking about this problem, this was in 1923. While he was thinking about this problem, this was during his PhD days. He came up with the solution that okay, electrons might be waves, and his PhD advisor, under whom he was doing his PhD, could not differentiate. Could not quite understand this proposition. He felt that this was pretty nice because it solved a lot of problems. He had shown in his thesis that it solves all the problems that they were having using the particle description. But he was not quite convinced. How can it be both particles and waves? So he sent the PhD thesis to Einstein, who was one of the leading physicists at that time, and sent it to Einstein. And Einstein said, this person does not deserve a PhD, he deserves a Nobel Prize. This idea is so brilliant that it's not just a PhD idea, it's a Nobel Prize idea. Louis de Broglie did get a Nobel Prize later on for this very idea. So the idea of complex waves, the idea of waves being associated with particles, is actually Louis de Broglie, but it took the genius of someone called Max Born later on in the 1930s in order to come up with a proper interpretation of what this meant. So 1920s were boom time for quantum physicists. They were not known as quantum physicists because you didn't have a quantum theory as such. It was just starting to form, and in 1926, 1927, these people, Heisenberg, Schrödinger came up later. Heisenberg, Schrödinger, Max Born, these people came up with one good description after another, and quantum theory was formulated. It's fascinating to read the history of quantum theory and its development in 1920s. Okay, so the next question which we asked last class is whether they can be both particles and waves, and we saw that they can really be. The electron is really a particle, but it's distributed like a wave. So the distribution is like a wave. It arrives like a particle. It turns out that both are correct descriptions, but we will be using the wave descriptions because the waves are easier to handle. We can just add up and square, and that's very easy. Also, explaining interference is very difficult with particles. It's almost impossible, but it's very trivial with waves. You just add up the waves and square it, right? It's very simple. We know the mathematics. The mathematical machinery is very simple, very easy. Now we also asked what the wave function is. and we know that this is not an electric field waving about, it's not a water wave waving about. This is it's a probability wave, so it's a probability amplitude, and the square of the wave function, it represents the probability density. Okay, so this one slide, I think it gives you a summary of all that has been said in today's class. It's been a very heavy lecture, this one, but we are going in leaps and bounds, and we are jumping into quantum mechanics. Quantum mechanics is full of new ideas. What we are missing, however, is we have to formulate these ideas into proper mathematical um, terms. So, and that proper mathematical terms will come in the next lecture or so, which will be this week itself. So lecture 2 will be more about the mathematics of this kind of formalism. I'll introduce you to something called abstract objects, what psi is, what psi of x is, and how we go about describing these kind of systems using the mathematics, using the new type of mathematics, probably one which you haven't seen before. So that will be in the next lecture. See you then, and hopefully I'll see you in next week when we continue after the mathematical formalism is just a little bit developed. Thank you.